A star dies in a cataclysmic explosion, scattering the seeds of life across the cosmos. This violent end is not a final act, but a crucial step in the universe's grand cycle of destruction and rebirth. Understanding this cosmic recycling program reveals our true place in the cosmos. By the end of this journey, you will see the universe not as a static void, but as a dynamic, self-renewing engine. We will trace the path from stellar life cycles to the ultimate fate of galaxies, uncovering how the iron in your blood and the calcium in your bones were forged in such stellar furnaces. What does it mean that everything we are was born from catastrophe and is destined for transformation once more? The early universe was a starkly simple place, a vast expanse filled with only the two lightest elements, hydrogen and helium. From this primordial soup, it seemed impossible that the incredible diversity of planets, oceans, and life could ever emerge. Yet within this apparent simplicity lay the potential for everything we know, waiting for the right conditions to unlock it. That key was the star itself, a cosmic forge whose internal machinery would build the periodic table from scratch. This process is called stellar nucleosynthesis, the universe's primary foundry. It is here, in the hearts of stars, that the raw materials for everything are crafted. As the astrophysicist Carl Sagan so eloquently put it, we are made of star stuff. This is not merely a poetic statement, but a scientific fact. Every atom of carbon in your cells, every molecule of oxygen you breathe, was forged in the fiery heart of a long-dead star. The process begins with the immense gravitational pressure at a star's core, crushing hydrogen atoms together with such force that they fuse, creating helium and releasing the energy that makes the star shine. This is the same process that powers our sun. In stars more massive than our own, this factory does not stop there. Once the hydrogen fuel is depleted, the core contracts, raising the temperature even further, until it becomes hot enough to fuse helium atoms into carbon. Then, layer by layer, new fusion reactions ignite. Carbon fuses into oxygen and neon. Oxygen fuses into silicon. This chain of creation continues, building ever heavier elements in concentric shells like the layers of an onion, all the way up to iron. Iron is a turning point, a product of this magnificent forge that also signals its end. Fusing iron does not release energy, it consumes it. This foundational act of creation, building complexity from simplicity, sets the stage for a dramatic and necessary catastrophe. The star is now sitting on a cosmic time bomb, having meticulously crafted the very elements that will lead to its own destruction. Iron marks the end of the line for the star's quiet factory. With its core now a lump of iron ash, the star's primary energy source vanishes. Gravity, held at bay for millions of years, wins in an instant. The star's core collapses in less than a second, falling inward at a quarter the speed of light. The rebound from this catastrophic collapse creates a shockwave of unimaginable power, and the star explodes. For a few glorious weeks, this single supernova can outshine its entire host galaxy, a final, defiant blaze of cosmic light. Yet this is not merely a death. This is the universe's ultimate act of distribution. The titanic forces and energies involved in this explosion are so extreme that they forge the elements that the star itself could never create. In that fleeting, brilliant fireball, atoms are smashed together with such violence that every element heavier than iron is born. The gold in a wedding ring, the uranium deep within the earth, the iodine essential for life, all are minted in this single, spectacular catastrophe. Then, the supernova's shockwave acts as a cosmic farmer, scattering this newly enriched material far and wide. It blasts these elemental seeds across light years, injecting them into the vast, cold clouds of gas and dust that drift between the stars. This act of destruction is what enriches the cosmos, seeding the void with the very ingredients needed for new solar systems to form. The fury of the supernova gives way to a period of quiet gathering, as gravity begins its slow, patient work on these newly scattered ashes. These beautiful, swirling clouds of cosmic dust and gas are far more than just celestial artwork. They are the universe's recycling centers in their most active and vibrant phase. After a supernova's violent scattering, this is where the gathered material finds a new purpose. Drifting for eons, the enriched debris from countless stellar explosions slowly accumulates, drawn together by the faintest of all cosmic forces, gravity. Over millions of years, this gentle, relentless pull coaxes the gas and dust into ever denser pockets. Within these dark, cool clouds, the seeds of new stars and planets begin to sprout from the ashes of the old. Look no farther than the Orion Nebula, a stellar nursery visible even through a small telescope. There, we see the process unfold in real time, with newborn stars, called protostars, igniting within the glowing veils of recycled material. Their brilliant light illuminates the very gas cloud that gave them birth. This is the magnificent creation phase of the cycle, where chaos slowly gives way to order, and the promise of new worlds emerges. From the generic beauty of a nebula, we can trace this story directly to our own origins. Our solar system, with its vibrant sun and orbiting planets, was once just such an unremarkable cloud of dust, a cloud that held within it the specific remnants of long-dead stars. That gold in a wedding ring has a violent history. Every single atom of it was forged not in the calm heart of a star, but in the cataclysmic final moments of a supernova explosion that occurred billions of years ago. The iron that carries oxygen in your blood, the calcium that strengthens your bones, these two are ancient stardust, the scattered remnants of a massive star that lived and died long before our own sun was even a glimmer in the cosmos. Our entire solar system is a case study in cosmic recycling, a direct product of that grand cycle of destruction and rebirth. In fact, we owe our very existence to a nearby catastrophe. Scientists hypothesize that the shockwave from a supernova, rippling through our region of space, acted as a cosmic trigger. It compressed a vast, dormant cloud of gas and dust, a cloud already enriched with the ashes of previous generations of stars. This compression kick-started the gravitational collapse that formed our sun at its center. As the young sun ignited, the remaining material swirled around it in a vast, flat disk. Within this protoplanetary disk, the next phase of construction began. Microscopic dust grains, each one a speck of recycled stardust, began to collide and stick together. Over time, these tiny clumps grew into pebbles, then rocks, then mountain-sized planetesimals. In a relentless game of cosmic bumper cars, these bodies merged, eventually assembling the planets, asteroids, and comets we know today. This means the Earth beneath your feet, the air you breathe, and every part of you is composed of material that was processed through at least one previous stellar generation. We are not just living in the universe, we are literal pieces of it, temporarily assembled into conscious form. This intimate, local story of our origins is just a single example of a process operating on a truly galactic scale. This grand cycle of stellar life and death is not an isolated event, but a rhythm that pulses throughout our entire galaxy. The Milky Way itself acts as a colossal recycler, a spinning engine of cosmic renewal. Its magnificent spiral arms are the key to this process, yet they are not what they appear to be. You might picture them as permanent structures, like the spokes of a wheel, but they are something far more dynamic. They are density waves, vast ripples of compressed space that sweep through the galactic disk. Think of them like a traffic jam on a cosmic freeway, or a wave moving through a field of tall grass. The individual blades of grass bend and then return to their position, but the wave itself moves forward. In the same way, stars and gas clouds move into a spiral arm, are compressed within it for a time, and then move out the other side as the wave travels on. It is this act of compression that is so vital. As a giant cloud of interstellar gas enters the crowded spiral arm, the wave squeezes it, triggering a chain reaction. The increased pressure causes pockets within the cloud to collapse under their own gravity, igniting the fires of new stars. This is why the spiral arms appear so bright and blue. They are lined with stellar nurseries, the galaxy's most active construction zones. But this galactic engine requires fuel. As new stars are born, older stars are constantly returning their processed material to the reservoir of space. A sun-like star, in its final peaceful stages, will gently puff its outer layers back into the void through a beautiful planetary nebula. More massive stars will blast their enriched guts back into the mix through powerful stellar winds and ultimately supernova explosions. This returned material is no longer simple hydrogen and helium. It is now seeded with carbon, oxygen, iron, and all the other elements forged in stellar cores. This enriched gas then becomes the raw material for the next generation of stars and planets, all stirred together by the galaxy's slow rotation. It is a continuous, galaxy-wide cycle, ensuring that no atom is ever truly wasted, but is instead perpetually remixed into new cosmic forms. This magnificent, self-sustaining process sets the stage for even more violent and energetic events that can reshape entire galaxies. The gentle, persistent recycling of our galaxy is just one part of a much grander, more turbulent story. On the largest cosmic scales, entire galaxies themselves are destined for collisions of breathtaking scope. Far from being a destructive end, these galactic mergers are among the universe's most powerful acts of creation. In about 4.5 billion years, our own Milky Way is set to experience this firsthand when it meets its colossal neighbor, the Andromeda galaxy. The image of two giant star systems crashing together might conjure visions of stellar fireballs and cosmic chaos, but the reality is both more subtle and more profound. The spaces between stars are so vast that direct collisions are almost unheard of. Instead, the real drama unfolds through the invisible force of gravity. As the galaxies make their first close pass, their mutual gravitational pull begins to violently stir the immense clouds of gas and dust that drift within them. This is where the transformation begins. This gravitational agitation compresses these vast gas clouds, triggering a ferocious wave of new star formation. It is a stellar baby boom on a galactic scale, where thousands, even millions of new stars ignite in a brilliant, widespread firestorm of creation. This burst of new life, however, comes at a cost. The same gravitational tides that give birth to new stars will also completely tear apart the majestic spiral structures of both galaxies. Over billions of years, their graceful pinwheels will be stretched and shredded, their stars scattered into a vast, swelling halo. The final product of this cosmic dance is not ruin, but rebirth. The two distinct spiral galaxies will merge into a single, new entity, most likely a giant elliptical galaxy, a smooth and featureless island of stars. This new galaxy, sometimes nicknamed Milkomda, will be a fusion of its predecessors, a fundamentally recycled structure built from their combined material. It is the ultimate demonstration that catastrophe and creation are two sides of the same coin, even for the largest structures in the cosmos. But what is the primal engine, the original power source, that set this entire magnificent cycle in motion? But what of the black hole, that most feared of cosmic monsters? For decades, we have viewed these gravitational pits as the ultimate end of the line, the universe's final trash compactors from which nothing, not even light, can escape. This terrifying image, however, is only half the story. Emerging research now paints a far more complex and surprising portrait, one where supermassive black holes act not as destroyers, but as master regulators, the ultimate recyclers in the galactic ecosystem. At the heart of nearly every large galaxy, including our own Milky Way, slumbers one of these colossal beasts, containing the mass of millions or even billions of suns. Their primary role is not to consume everything in sight, but to act as a cosmic governor, controlling the very pace of star formation. How do they achieve this? As vast clouds of gas are pulled toward the galactic center by the black hole's immense gravity, they don't all fall in. Instead, some of this infalling matter is funneled into powerful, rotating disks, and a fraction of it is then channeled and blasted back out into space in the form of searing jets and winds of radiation. These outflows travel at nearly the speed of light, carrying a phenomenal amount of energy. This energy does not destroy the galaxy, it heats it. It acts like a giant cosmic furnace, keeping the enormous reservoirs of gas surrounding the galaxy too hot and turbulent to collapse easily and form new stars. This creates a delicate feedback loop, a self-regulating system. If too much gas begins to cool and form stars, the central black hole feasts on the excess, becoming more active and firing its jets with greater ferocity. These jets then heat the surrounding gas, effectively turning off the star formation tap. When things calm down, the tap can slowly turn back on. This means the black hole is not a passive consumer, but an active participant, recycling matter and energy on a galactic scale to maintain balance. It prevents the galaxy from either burning through its fuel too quickly in a starburst frenzy or from stagnating entirely. The matter that falls in may be lost forever, but its gravitational energy is converted and repurposed, blasted back out to shape the destiny of everything around it. This profound realization forces us to confront the deepest mystery of all. What is the ultimate fate of all this matter and information that crosses the black hole's threshold? And what does it mean for the final act of cosmic recycling? This leads us to a deep and troubling puzzle. If a black hole devours a star or a planet or even a book, what happens to the information that made that object unique? According to the classical laws of physics, that information is gone forever, locked behind the event horizon. This idea clashed violently with the principles of quantum mechanics, which state that information can never be truly destroyed. This conflict became known as the information paradox, a fundamental problem that threatened to unravel our understanding of reality. Stephen Hawking tackled this paradox with a revolutionary idea, one that forever changed our view of black holes. He proposed that they are not the eternal prisons we once thought. Through a strange and subtle quantum process, black holes can slowly leak their mass back into the universe. This phenomenon is called Hawking radiation. The process unfolds in the ghostly quantum foam that fills empty space, where pairs of virtual particles and antiparticles constantly flicker in and out of existence. Normally, these pairs annihilate each other almost instantly, but right at the very edge of a black hole's event horizon, something different can happen. One particle of the pair might fall across the boundary, while the other escapes into space. The escaped particle becomes real, carrying away a tiny amount of the black hole's energy. From the outside, it appears the black hole is glowing, emitting a faint whisper of heat. This slow, steady leak means that over unimaginable eons, a black hole will eventually evaporate, returning all of its mass energy to the cosmos. But here the paradox sharpens to a fine point. The radiation escaping seems to be purely random, a featureless thermal fuzz that contains no information about what fell in. So when the black hole finally vanishes, where did all that specific information go? Was it truly erased from the universe? Most physicists today believe the information must be preserved, perhaps imprinted in some scrambled form on the radiation itself or on the event horizon. The debate continues, a frontier of modern physics. Yet even without a final answer, Hawking's revelation is profound. It suggests that not even a black hole is a final destination. It is a temporary vault, a cosmic transformer that eventually returns what it has taken, albeit in a form we cannot yet decipher. The most absolute destruction we can conceive of is, in fact, part of the cycle. This quantum whisper from the void, the slow evaporation of spacetime itself, brings our journey to its final, breathtaking scale. To understand the ultimate fate of this grand cycle, we must first look back to its absolute beginning. Rewind the cosmic clock nearly 14 billion years, to a time when the entire universe was not cold and dark, but a searing, brilliant fireball. It was an ocean of raw energy, a thick, opaque plasma so dense that light particles could not travel any meaningful distance without being instantly absorbed and re-emitted. The universe was a glowing fog, with no stars, no galaxies, and no clear path for light to escape. Then, about 380,000 years after the Big Bang, a pivotal event occurred. The expanding cosmos had cooled just enough for a fundamental shift. Electrons combined with atomic nuclei, forming the first stable atoms, primarily hydrogen. In that moment, the universe suddenly became transparent. The light that had been trapped within that primordial soup was finally set free, streaming across space in every direction. This first flash of liberation is what we detect today as the cosmic microwave background. It is the oldest light in existence, a fossilized snapshot of the infant universe, cooled and stretched by eons of expansion into a faint microwave whisper that uniformly bathes the entire cosmos. But this cosmic baby picture is not perfectly smooth. When we map it with incredible precision, we find it is modeled with tiny variations, minuscule hot and cold spots that represent regions of slightly higher and lower density. These fluctuations are the most important part of the story. They are the original seeds of destiny, those slightly denser patches, imprinted by quantum ripples from the universe's first moments, held just a little more gravitational pull. Over billions of years, that extra tug drew in surrounding matter slowly, inexorably building the cosmic structures we see today. Every galaxy cluster, every swirling spiral, every solitary star exists because of these initial imperfections. The blueprint for all cosmic recycling, for the great dance of nebulae, stars, and supernova, was stamped into the fabric of reality at the very dawn of time. This ancient relic shows us that creation and structure are inherent properties of our universe, but it also points toward a far more desolate and distant future, a time when the cycle itself may finally run down. This grand cosmic cycle of rebirth, fueled by stellar explosions and galactic collisions, cannot run forever. Every engine requires fuel, and the universe's primary fuel is the simplest element of all, hydrogen. As the cosmos continues its relentless expansion, this fundamental resource is being stretched ever thinner across an immense and growing volume. Galaxies are like islands in this expanding sea, and their reservoirs of free hydrogen gas, the raw material for new stars, are finite. They are being consumed in the ongoing process of star formation, and not being replenished at the same rate. The brilliant blue-white giants that light up spiral arms are the most profligate, burning through their hydrogen in just a few million years. But even the most frugal red dwarf will eventually exhaust its core. We are living in the universe's golden age of star formation, a period of vibrant cosmic activity that will not last. The future holds a slow, irreversible dimming. Over trillions of years, the majestic spiral galaxies we see today, vibrant with stellar nurseries, will transform. Their gas will be depleted, either turned into stars or blown away by supernova and black hole winds. Without this fresh material, the spiral arms will fade. These dynamic engines of creation will settle into quieter, more sedate elliptical galaxies, where star formation has all but ceased. The sky will grow darker. The last new stars will have flickered to life eons earlier. What remains will be a cosmos populated by the aging and the dead. Red dwarfs, those faint, miserly stars, will glow for trillions of years, but even their fires will eventually sputter out. The universe will become a graveyard of white dwarfs, neutron stars, and black holes, all that is left of the stellar giants of a bygone era. This is the long-term forecast, a slow and inevitable winding down of the primary creative engine we have followed throughout this story. It is not a dramatic explosion, but a gradual fade, a descent into a deep and profound cold. Yet, even in this final state, the universe may not be entirely finished with its work of transformation. Even after the last star flickers out, the universe is far from empty. It will be populated by the extraordinary remnants of stellar lives, objects so strange they defy imagination. The most common of these will be white dwarfs. Picture the core of a star like our Sun, a fiery engine that once fused hydrogen into helium. When such a star dies, it gently sheds its outer layers, leaving behind its naked core, a sphere of white-hot carbon and oxygen. This is a white dwarf. Though it contains the mass of a star, all that matter is crushed into a volume no larger than Earth. A single teaspoon of its material would weigh many tons here on our planet. These stellar embers no longer generate new energy through fusion. They simply glow with the leftover heat of their former lives, destined to cool over trillions of years. They are the ultimate cosmic cinders, slowly fading from white to yellow to red, and finally to invisible black dwarfs, cold and dark. This final state is purely theoretical, a ghost in the future of the cosmos, because the universe is not yet old enough for even the first white dwarf to have reached this absolute zero. Alongside these common remnants will be far more exotic relics, the neutron stars. Born in the violent crucible of a supernova, a neutron star is what remains when a massive star's core collapses. The force of that collapse is so immense that it smashes protons and electrons together, fusing them into neutrons. An entire star, more massive than our Sun, is compacted into a perfect sphere just a dozen miles across. It is a single, city-sized atomic nucleus. A sugar cube-sized piece of this material would weigh as much as every human on Earth combined. In this state, matter is frozen, its atomic structure utterly erased. There is no empty space, just a solid, unimaginably dense sea of neutrons. These objects are the definitive endpoint for a vast amount of the universe's normal matter, stable for timescales that dwarf the current age of the cosmos. They are the final, inert products of stellar recycling, the ultimate cosmic tombs. But in this seemingly permanent graveyard, could there be one last, spectacular act of recycling waiting in the dark? Yet even these cosmic tombs are not necessarily eternal. Deep within the heart of a neutron star, or locked inside the cold, dark matter of a black dwarf, the very building blocks of atoms may hold a final, startling secret. The proton, one of the fundamental particles that makes up every atomic nucleus, has always been considered a bedrock of stability. It is the cornerstone of all normal matter, the unchanging anchor in the swirling sea of quantum particles. But what if even the proton is not immortal? Enter one of the most profound and speculative ideas in all of physics, the hypothesis of proton decay. Some grand unified theories which attempt to merge the fundamental forces of nature predict that the proton is not perfectly stable. It could, over timescales so vast they defy human comprehension, spontaneously decay. The predicted half-life for a proton is staggering, perhaps 10 to the power of 34 years or longer. To put that incomprehensible number in perspective, it is a 1 with 34 zeros after it, a duration that makes the current age of the universe seem like a single blink in an endless eternity. If this theoretical process is real, then no structure made of matter is truly permanent. Not planets, not asteroids, and not even the seemingly indestructible neutron star. A neutron star, for all its incredible density, is still made of matter, and that matter is composed of particles like protons and neutrons. If protons can decay, then even this city-sized atomic nucleus would slowly, imperceptibly evaporate. Its immense mass would transform, not in a flash, but in a slow leak of energy and lighter particles, returning its substance to the universe in the most fundamental way possible. This would be the ultimate, final act of cosmic recycling. After the stars have died and the galaxies have faded, this process would work over eons to dismantle the last complex structures. It would break down every atomic nucleus, every last remnant of what was once a star or a planet, into a diffuse, thin sea of subatomic particles and radiant energy. The universe would become a cold, dark, and incredibly simple place. This speculative concept pushes at the very edge of our understanding, forcing us to question a foundational assumption. Is anything in this grand, cyclical universe truly permanent, or is everything, from a fleeting thought to a neutron star, merely temporary in the endless flow of transformation? But for all its grandeur, this cosmic cycle of stars and galaxies rests upon an invisible foundation. The matter we can see and touch, the stuff of planets and people, accounts for less than 20% of all the matter in the universe. The rest is a profound mystery, an unseen substance known as dark matter. It does not emit, absorb, or reflect any light, making it completely transparent to our telescopes. We cannot see it, but we can feel its gravitational pull. In fact, its ghostly presence is the primary reason our universe looks the way it does. After the Big Bang, the slight ripples in the cosmic background radiation were not enough on their own to pull together the vast structures we see today. Dark matter provided the necessary gravitational anchor. It collapsed first into a vast, invisible web, a cosmic skeleton stretching across the void. The normal matter, the hydrogen and helium gas, simply flowed into the gravitational wells created by this dark scaffold. Without this unseen framework, galaxies might never have formed, and the great cycle of stellar life and death would have been a far more scattered and inefficient affair. Every galaxy, including our Milky Way, is now embedded within a gigantic halo of this dark matter, a vast sphere that extends far beyond the visible stars. This halo acts like a gravitational glue, holding the galaxy together and dictating its rotation. It is also the unseen hand that guides the fate of galaxies during collisions. When the Milky Way and Andromeda merge, it will not be a collision of stars, but a profound interaction of their immense dark matter halos. Their gravitational dance will choreograph the entire merger, stirring the gas and triggering the starbursts that will reshape both galaxies. So while dark matter itself never forms stars or planets, it creates the conditions, the stages, and the gravitational rules that allow the visible universe to continually recycle itself. This silent, dominant partner in the cosmic dance raises a pivotal question. If gravity is the great architect, pulling everything together, what force could possibly work against it on a universal scale? Gravity, the great architect of cosmic structure, now faces a formidable and mysterious rival. While dark matter pulls the universe together, an even more dominant force is working to tear it apart. This is dark energy, the most profound puzzle in modern cosmology. It is not a substance we can detect or measure directly, but rather a property of space itself, a kind of latent pressure woven into the very fabric of the cosmos. Its sole, staggering effect is to push the universe apart, causing its expansion to accelerate over time. For billions of years, gravity has been the dominant force on the galactic stage, pulling matter together to build stars, galaxies, and clusters. But dark energy represents a fundamental shift in the balance of power. Think of it as a cosmic tide that is slowly but surely rising, pulling the islands of matter further and further away from one another. This accelerating expansion does not rip apart individual galaxies, which are bound together by their own gravity. Instead, it works on the vastest scales, increasing the distances between entire galaxy clusters. Where gravity builds, dark energy disperses. This creates a cosmic tug-of-war that will define the ultimate fate of everything. As the expansion accelerates, the universe becomes a lonelier place. The grand galactic collisions that have been so vital for triggering new waves of star formation will become increasingly rare, and then impossible. Galaxies that are not already bound by gravity will be swept away from each other by the stretching of space itself, moving beyond each other's cosmic horizons. Over trillions of years, this accelerating force will effectively quarantine the remaining islands of matter. Each galaxy, and eventually each galaxy cluster, will become isolated, floating in a vast and ever-growing void. The grand cycle of galactic recycling, the beautiful dance of creation and destruction that has shaped our cosmos, will slowly grind to a halt. The universe's primary engine of renewal will be starved of the raw material and the gravitational interactions it needs to continue. This is the fundamental tension at the heart of our cosmos, a battle between the creative, gathering force of gravity and the dispersing, isolating force of dark energy. One force builds the intricate structures that allow for stars and planets, while the other ensures that those structures will one day drift alone in an unimaginably vast and cold darkness. This same principle of cosmic renewal operates right beneath our feet. Our planet Earth is a master recycler in its own right, running intricate systems that maintain the very conditions for life. The ground you stand on is not a permanent foundation, but part of a slow, churning conveyor belt of rock. Deep within the Earth, immense heat drives the engine of plate tectonics. Giant slabs of the planet's crust, some bearing entire continents, drift on the molten mantle below. Where these plates collide, one can be forced downward, sliding back into the planet's interior in a process called subduction. The rock of the old ocean floor, along with any sediments and even water locked within it, is pulled deep into the mantle. There, under extreme heat and pressure, it melts, becoming part of the mantle's slow, convective churn. This is not a final grave. That recycled material will eventually find its way back to the surface, rising in plumes of magma to burst forth from volcanoes as new land, or solidifying at the boundaries of tectonic plates to create fresh crust. This is the rock cycle, a planetary-scale renewal system that has been running for billions of years. The very continents we live on are built from the remains of ancient sea floors, constantly remade and reshuffled. But the planet's recycling genius does not stop with rock. Our atmosphere is also part of a delicate, self-regulating loop, the carbon cycle. Carbon dioxide in the air is absorbed by the oceans, where it is used by marine organisms to build their shells. When these creatures die, their shells sink to the seabed, forming layers of limestone, effectively locking the carbon away in rock. This process naturally cools the planet over geological time. Then, the tectonic cycle completes the loop. When that seafloor is subducted back into the mantle, the intense heat breaks down the limestone, releasing the stored carbon. This carbon then travels back up through the crust, venting into the atmosphere through volcanic eruptions, ready to begin the cycle anew. This planetary thermostat has kept Earth's climate relatively stable, preventing it from freezing over or boiling away for eons. So the stability that allows life to flourish is not a static gift, but a dynamic balance maintained by relentless, grinding, planetary-scale recycling. The grand cosmic dance of creation from Catastrophe finds a direct, intimate echo in the very ground we walk on and the air we breathe. The very asteroids and comets we fear as agents of destruction may, in fact, have been our cosmic delivery service. For billions of years, the narrative of these impacts has been one of pure catastrophe, like the event that ended the reign of the dinosaurs. But we must look further back, to the violent infancy of our solar system, to see their creative potential. During a period known as the Late Heavy Bombardment, the inner planets were pummeled by a relentless rain of asteroids and comets. The young Earth was a scorching, largely sterile world, its surface a molten hellscape repeatedly resurfaced by these colossal collisions. It seems like a recipe for permanent desolation. Yet, paradoxically, these same cataclysmic impacts may have delivered the very ingredients that made our world a living planet. Icy comets, in particular, are thought to be rich reservoirs of water. With every impact, they could have released torrents of water vapor into the atmosphere, eventually cooling and falling as rain to fill the first oceans. But they brought more than just water. We now know that asteroids and comets can be laden with complex organic molecules, the fundamental building blocks of life. Amino acids, the components of proteins and nucleobases, the letters of our genetic code, have been found in meteorites that have fallen to Earth. This presents a staggering possibility. The raw materials for biology, the very same chemistry that would eventually spark into life, might have been seeded on our planet from the depths of space. This idea stretches even further into the realm of a theory called panspermia. It suggests that life's building blocks, or perhaps even dormant microscopic life itself, could hitch a ride inside the protective rock of an asteroid or the icy heart of a comet. A collision on one world could blast material containing these hardy spores into space, where it could travel for millions of years before another impact delivers it to a new, fertile world. In this view, life may not be a singular miracle on Earth, but a cosmic inevitability, a passenger on a grand tour of the galaxy, spread by the very catastrophes that seem to spell its end. This bridges the vast gap between cosmic evolution and biological evolution, revealing that the universe does not merely recycle matter, but potentially sows the seeds of life itself through its most violent processes. Our own sun is a ticking clock, a quiet recycler whose ultimate fate is written in the same laws that govern every star. Right now, it is in the most stable and long-lived phase of its life, the main sequence. For the past 4.5 billion years, it has been faithfully fusing hydrogen into helium in its core, releasing the steady stream of energy that has made our world a living planet. This calm period will last for another 5 billion years or so, a testament to the beautiful equilibrium between the outward push of fusion and the inward crush of gravity. But this balance is temporary. When the sun's core finally exhausts its hydrogen fuel, that delicate equilibrium will shatter. The core, no longer supported by fusion's energy, will begin to contract under its own immense weight. This collapse will generate intense heat, raising the temperature so dramatically that the shell of hydrogen surrounding the core will ignite in a furious new wave of fusion. The energy from this shell burning will be overwhelming. It will push the sun's outer layers outward with irresistible force, causing our star to bloat to a colossal size. It will become a red giant, swelling to over 100 times its current diameter. Its outer atmosphere will stretch outwards, its fiery tendrils reaching across the inner solar system. Mercury will be the first to vanish, swallowed whole and vaporized in an instant. Venus will follow, its thick atmosphere offering no protection from the stellar inferno. And then, it will be Earth's turn. Our world, the only home we have ever known, will be seared and engulfed. The oceans will boil away, the rock itself will melt, and the planet will be utterly dismantled, its atoms becoming part of the sun's expanding atmosphere. This is the ultimate act of local destruction, the end of the world written in stellar physics. Yet this is not the end of the sun's story, nor the end of its role in the cosmic cycle. After its red giant phase, the sun will undergo a final, beautiful transformation. It will pulse violently, shedding its outer layers not in a supernova, but in a series of gentle heaves. These expelled shells of gas, illuminated by the hot core they leave behind, will blossom into a magnificent planetary nebula. For a few tens of thousands of years, this glowing cloud of multicolored gas will be a beacon in the galaxy, a final farewell. Within that nebula, drifting amidst the incandescent hydrogen and helium, will be the newly forged atoms of carbon, nitrogen, and oxygen that were created in the sun's final fiery stages. The iron in our blood and the calcium in our bones will be safe, locked in the white dwarf that remains, but these lighter, vital elements will be returned to the cosmos. What was once the star that gave us life will become the fertilizer for future worlds. The white dwarf core, an Earth-sized diamond of degenerate matter, will be all that is left, a dense ember that will slowly cool over trillions of years. Our solar system will be gone, but the Sun's legacy will be written in the enrichment of a nearby molecular cloud. Its death ensures that someday, from that enriched cloud, a new star will ignite, perhaps with rocky planets of its own, and the grand, relentless cycle of cosmic recycling will begin anew, all thanks to the final, generous act of our own familiar Sun. This intricate cosmic dance forces a profound question. What if the universe's ability to recycle itself is not just a fortunate accident, but a fundamental requirement for our own existence? This line of thinking leads us to the anthropic principle, a philosophical and scientific idea that can feel both illuminating and unsettling. It suggests that the fundamental constants of our universe, the very rules of physics, appear to be exquisitely fine-tuned. The strength of gravity, the force binding atomic nuclei, the mass of an electron, these values are not random. They seem to have been set with a startling precision, all seemingly arranged to allow for the emergence of stars, planets, and ultimately, living observers. Consider the force that holds atomic nuclei together, the strong nuclear force. If it were just a few % weaker, protons could not stick together. Hydrogen would be the only element, and the complex atomic nuclei that form stars and planets would never have coalesced. The cosmic recycling program would have stalled before it even began. Conversely, if this force were slightly stronger, protons would bind together too easily. Hydrogen would have fused into heavier elements instantly after the Big Bang, leaving no long-lasting fuel for stars. The universe would have burned out in a quick, brilliant flash, with no slow, steady stellar lifetimes to build the elements of life. Even the specific properties of carbon, the essential backbone of biology, are a testament to this fine-tuning. For carbon to form inside stars, its nucleus must exist in a very specific, excited state that allows 3 helium nuclei to fuse together efficiently. Without this precise and unlikely nuclear resonance, the universe would be starved of carbon. There would be no organic chemistry, no life as we know it. The chain of creation that builds from carbon to oxygen and beyond would simply fail. So the supernova, the nebula, the formation of new solar systems, all these steps in the grand cycle rely on a deeply rooted cosmic harmony. The anthropic principle offers a reflective, almost circular, explanation. We observe a universe capable of complex recycling because only such a universe could have produced us to be the observers. It connects the colossal physical processes of stellar death and rebirth directly to the intimate mystery of our own consciousness. We are not just passive witnesses to this cycle, we are its products, living evidence that the universe possesses the specific rules necessary to turn catastrophe into creation and stardust into sentience. This search for our own cosmic origins now extends far beyond our solar system, into the atmospheres of distant worlds. Astrobiology, the science of seeking life in the universe, is fundamentally a hunt for the ultimate evidence of cosmic recycling. The clues we seek are called biosignatures, and they are not little green men, but subtle chemical fingerprints. The most telling of these is an atmosphere that is chemically out of balance. On Earth, our air is a bizarre and unstable mixture. We have large amounts of oxygen, a highly reactive gas that should quickly bind with other elements and vanish from the atmosphere. The only reason it persists is because life, through photosynthesis, constantly pumps it back into the air. Even more telling is the simultaneous presence of oxygen and methane. These two gases react with each other and should destroy one another. Finding them together in a planet's air is a powerful sign that something, most likely life, is actively and continuously replenishing both. Every atom of that oxygen, every molecule of that methane, is a product of the grand cycle. The oxygen was forged in a massive star that lived and died long before our sun was born. The carbon in the methane was created in that same stellar forge and scattered by a supernova's blast. When we point our telescopes at an exoplanet and analyze the light filtering through its atmosphere, we are not just looking for life. We are checking to see if the recycled materials from stellar cataclysms have been assembled into something new, something that maintains its own dynamic, complex chemistry. This quest is not limited to distant suns. Within our own cosmic backyard, missions are being designed to probe the most likely places for this assembly to have occurred. The icy moons of Jupiter and Saturn, like Europa and Enceladus, are frozen worlds hiding a profound secret. Beneath their thick, cracked icy shells, vast global oceans of liquid water are thought to slosh against a rocky seafloor. These are not just puddles, but bodies of water that may contain more volume than all of Earth's oceans combined. The plumes of water vapor and organic molecules erupting from Enceladus's south pole are a direct sample of this hidden environment. They tell us that the essential ingredients for life, water, and complex chemistry, are present and being actively mixed. These subsurface oceans are the perfect laboratories, shielded from harsh radiation and warmed by the gravitational tug of their giant parent planets. A future robot, landing on the ice or flying through a plume, could look for the same chemical imbalances we seek in distant atmospheres. Finding life, or even just the complex prebiotic chemistry that precedes it, on such a world would be a monumental discovery. It would confirm that the universe's recycling program does not merely create the elements for life, but that it consistently sets the stage for life's emergence. We would no longer be a singular miracle, but a predictable, perhaps even common, outcome of a cosmos that is hardwired for renewal. The search for life is the ultimate test of whether stellar ashes can consistently ignite the spark of biological complexity. But this relentless rhythm of destruction and rebirth might not be confined to our single universe. The ultimate expression of cosmic recycling could be happening all around us, in a reality so vast we can only glimpse its edges through mathematics. This is the multiverse hypothesis. Picture our entire cosmos not as the entirety of existence, but as a single bubble floating in an infinite, frothing sea of reality, a meta-universe in a state of eternal, hyper-fast inflation. In this staggering view, the Big Bang was not the absolute beginning, but simply the moment our particular bubble of space-time formed and began its own internal expansion. And just as bubbles form in a boiling pot, new universes are constantly nucleating in this greater beyond, each one a separate pocket reality. The rules inside each bubble could be utterly different. In one universe, gravity might be 1,000 times stronger, instantly crushing any possibility of stars or planets. In another, the nuclear forces might be too weak to form atoms at all. Our universe, with its finely tuned constants perfect for stellar life cycles and carbon-based life, might simply be one lucky ticket in an infinite cosmic lottery. Another theory, the cyclic or Big Bounce model, suggests an even more direct form of universal recycling. It proposes that when our universe expands to its maximum size, dark energy could decay, allowing gravity to pull everything back together in a big crunch. But instead of ending in a singularity, the universe rebounds, launching a new Big Bang from the ashes of the old one. In this model, time itself has no true beginning or end, just an endless, breathing rhythm of expansion and contraction. Each cycle erases the specific structures of the past, but the fundamental stuff of reality is preserved and reborn, ready to form new galaxies, new stars, and perhaps new life under a slightly different set of physical laws. This pushes our journey to its ultimate, mind-bending limit. The cycle we have traced from stars to galaxies might be a mere subroutine in an infinitely larger program, where entire cosmos are born from catastrophe, and themselves become the raw material for the next. Gravity may be the great architect of the cosmos, but it does not work alone. An invisible force, far weaker yet profoundly influential, weaves through the void, guiding the flow of cosmic material. These are the magnetic fields that permeate the space between the stars. Born in the turbulent hearts of stars and amplified by the churning motions of interstellar gas, these fields create an unseen architecture throughout the galaxy. They are the ghostly threads on which the beads of creation are strung. When a vast cloud of gas begins to collapse under its own weight to form a new star, gravity may provide the initial pull, but magnetism dictates the final form. The magnetic fields create a subtle resistance, a kind of cosmic friction that slows the collapse and prevents the cloud from fragmenting chaotically. They channel the infalling gas into orderly streams and powerful jets, focusing the material onto the growing protostar at its center. We can see this process in action with newborn stars, which often fire brilliant, narrow beams of matter from their poles, piercing the surrounding nebula like cosmic blowtorches. These jets are propelled and collimated by the star's own twisted magnetic fields, carrying away excess energy and momentum, allowing the star to gather mass efficiently. This magnetic guidance system extends to the formation of planets within the swirling disk of dust and gas. The fields help stir the material, encouraging dust grains to clump together, and may even be responsible for creating the turbulence that builds the first planetesimals. On a far grander scale, the same principle operates at the heart of active galaxies, where supermassive black holes launch jets that stretch for thousands of light years. These colossal outflows, steered by magnetic fields, carry immense energy and magnetic influence far into intergalactic space. They can compress distant gas clouds, triggering new waves of star formation, or they can heat galactic halos, effectively turning the star-forming tap-off. This reveals a universe where the grand cycle of recycling is not a simple, gravity-driven crush, but a delicately orchestrated dance. It is a dance directed by invisible magnetic hands, ensuring that the ashes of dead stars are woven into new creations with both power and precision. For centuries, we have watched the silent movie of the cosmos, our eyes limited to the narrow band of light that reaches our telescopes. But now we have learned to listen. The universe is not silent. It thrums with vibrations, with the faintest whispers of spacetime itself. These are gravitational waves, ripples in the very fabric of reality, predicted by Einstein over a century ago, and finally detected for the first time in 2015. They are not made of light or matter, but of gravity itself, generated when massive objects undergo violent acceleration. Picture the effect of two black holes, each with the mass of dozens of suns, spiraling toward each other at nearly the speed of light. Their immense gravity warps the space around them, and as they finally collide and merge, they shake the cosmos, sending out a tremor that travels at light speed across billions of light years. These waves are incredibly faint by the time they reach us, stretching and squeezing the distance between objects by less than the width of an atomic nucleus. To detect them, we built the most precise rulers in history, laser-based observatories like LIGO and Virgo, which can sense these minute cosmic shudders. This gave us an entirely new sense, allowing us to hear the universe's most powerful catastrophes as they happen. Then, in 2017, our new ears witnessed something truly historic. We heard the distinctive chirp of two neutron stars, the ultra-dense remnants of dead stars, colliding in a galaxy 130 million light-years away. For the first time, we not only heard the event, but we also saw it. Telescopes around the world and in space swiveled to the same patch of sky, capturing the brilliant flash of light from the explosion. This multi-messenger astronomy, combining the feel of gravitational waves with the sight of light, confirmed a long-held theory in spectacular fashion. The analysis of that light revealed the unmistakable signature of newly forged elements, including vast amounts of gold and platinum. In that single observation, we had direct proof. The catastrophic merger of two dead stars was, in fact, a cosmic mint, a factory producing heavy elements and blasting them out into space. We were witnessing the universe's recycling machinery operating in real time, turning the most destructive events into the very materials that could one day form new worlds. Our ability to hear these ripples has transformed our understanding, revealing a cosmos that is constantly ringing with the echoes of creation born from collision. The image of a serpent eating its own tail, the Ouroboros, is one of humanity's oldest symbols. Across countless cultures, from ancient Egypt to Norse mythology and Eastern philosophies, we find this same profound truth echoed: the understanding that all things exist within a cycle of endings and beginnings. The phoenix rises from its own ashes, just as a nebula blooms from the dust of a dead star. We have spent this journey mapping the physics of this cycle, but its implications resonate far beyond the telescope, touching the very core of our human experience. The cosmos, in its grand, impersonal dance, teaches us the fundamental nature of impermanence. Stars that burn for billions of years are not permanent. Galaxies that seem like eternal fixtures will one day merge and transform. If entire worlds are temporary, then our own individual struggles, our losses, and our greatest triumphs are also part of this universal flow. This is not a message of futility, but one of profound liberation. The same cosmic laws that dictate a supernova's necessary death to seed new worlds also tell us that our own endings, however painful, are often the required catalysts for new growth. The universe operates on a simple, brutal, and beautiful principle: that stagnation is not an option. Change is the only true constant. When we internalize this cosmic perspective, our own lives are cast in a different light. The career that ends, the relationship that transforms, the personal identity that must be shed, these are not failures of a chaotic existence. They are the personal echoes of a universal process. We are not separate from the cosmos, subject to its whims. We are the cosmos, experiencing its own cyclical nature from the inside. The iron in your blood remembers its birth in a stellar catastrophe, and the carbon in your cells knows the quiet gathering of a nebula. To feel anxiety in the face of change is human, but to understand that change is the engine of all creation is to align yourself with the deepest truths of reality. This cosmic mirror shows us that destruction and creation are not opposites, but partners in an endless dance. Embracing this can transform our fear of the unknown into a quiet confidence, a trust in the process that built the very atoms of our being. Our story does not end with this philosophical reflection, for the very tools we use to observe the cosmos are now revealing an even more astonishing possibility: that the universe itself might be a single iteration in an infinite series of cosmic rebirths. These new observatories are not merely better telescopes, they are time machines. The James Webb Space Telescope, with its infrared eyes, is uniquely designed to catch the stretched, redshifted light from the most ancient stars. It peers back to an era known as the Cosmic Dawn, a time when the first stars were igniting, monstrous behemoths made only of hydrogen and helium. By studying their light and the composition of the very first galaxies, we are effectively reading the universe's original recipe, understanding the primordial conditions from which all subsequent recycling would flow. We will see the cycle in its purest, most violent form, witnessing the supernova of these first stars that initially seeded the cosmos with the first heavy elements. Simultaneously, here in our own cosmic neighborhood, the Vera C. Rubin Observatory will conduct a relentless, decade-long cinematic survey of the sky. Its enormous camera will capture the entire visible sky every few nights, creating a time-lapse movie of the universe. This grand inventory will catch stars in the act of dying, spotting supernova as they flare into existence and then fade. It will map the delicate structures of planetary nebulae and track the movements of countless stars, building a vast, dynamic census of stellar life and death. This local data provides the other half of the story, the modern efficiency of the process. By comparing the ancient universe with the contemporary one, we can measure how the cycle has evolved over billions of years. Has the rate of star formation changed? Are supernova creating elements in the same proportions now as they did in the past? Each new observation is a piece of evidence, helping us assemble a complete timeline of cosmic renewal. This is not a passive observation, but an active excavation of our own history, a quest to trace the entire lineage of the atoms that now allow us to contemplate the stars. From the violent death of stars to the quiet birth of new worlds, we have traced the universe's grand, self-renewing engine. It is a system of breathtaking efficiency, where every ending is woven directly into a new beginning. We are not merely inhabitants of this cosmos, passing through a static stage. We are an active, conscious part of its endless rhythm. The iron in your blood, the calcium in your bones, every atom that defines you, was forged in a distant stellar furnace and scattered by a cataclysmic explosion. One day, long after our sun has faded and Earth is a memory, these very atoms will be returned to the cosmic void. They will drift in the darkness, waiting for gravity's gentle pull to gather them once more, to become part of a new star, a new planet, or perhaps a new form of consciousness. This is the beautiful, humbling truth of our existence. We are the universe experiencing itself, a fleeting moment of awareness in an epic of perpetual transformation. It is a story of destruction and creation on a scale beyond human comprehension, yet it is the very story written in ourselves. We would love to hear your thoughts on this profound connection in the comments below. If you enjoyed this journey through the mysteries of the cosmos, please subscribe for more explorations into the wonders that surround